Good evening, everyone. My name is Arda, and today I'm going to talk about static typing and C++ interfacing in CPython. So basically the C implementation of the Python language. A bit of background about me and why I picked this topic is basically, I'm a postdoc until next weekend at KTH, and soon I will be working as a data scientist at Ericsson. And I work usually with asynchronous algorithms for big data problems and basically machine learning problems on spanning different computing nodes. And for this reason, I use mainly C++ and then Python and Julia in my work pipeline. And basically, whenever you use Python, you choose, I don't know, TensorFlow or Torch. It's always C++ behind the scenes, of course. So basically, in a sense, I'm mostly into C++. But then why I have prepared this presentation, I know, like me, and maybe even more than me, most of you mainly use C++. But I hope we often choose also dynamically typed or higher level languages to prototype or script. That I say I hope because I don't want to be the off-topic person right now, if that is not relevant for you. But anyways, we usually have friends who often choose these languages for some reason or another. And then in the end, we or our friends want to benefit from our C++ code in these higher level languages. So today I'll introduce Cython, from Cython in quotes, because that's the book's name. I gave this here basically the ISBN and such if you want to dig deep more. And then, so based on this book, I'll be going through how static typing with Cython is done in CPython, and then how we can interface. So what type of tools we have in Cython to interface already written C or C++ libraries, again in Cython. And then I will present a small demo, and the demo is basically borrowed from this ray tracing in 1 weekend series in this website, raytracing.github.io by Peter Shirley. So I have just finished chapters 1 to 6 in the first book. There are 3 books. It's a fun website. I think you can spend some time there if you are into this one. And that topic actually was proposed by Harold himself. So I just wanted to say, okay, maybe I can combine the two. I don't know. In the end, so in that demo, I will generate an HD background scene. And I will randomly place spheres on the scene, and then what ray tracing does is basically, right now there is no material involved. From each pixel from the scene that goes to our eye or to the camera, it calculates whether rays coming to the camera hits any of the spheres, and if yes, what is the closest point, so that we will just blend the color and then we will see the actual shapes in like 3D. So what is Cython? Cython is basically 2 closely related things from the book. Cython, with a capital C if you wish, is a programming language that blends CPython with static typing system of C and C++. And lowercase one, Cython, is the name of the compiler, which basically translates this Cython source code into efficient C or C++ source code. And this source code can then be compiled into a Python extension module or can be run independently as an executable. So this means because Cython is a superset of CPython, which basically keeps the Python language and just adds the static typing system of C and C++, every piece of CPython code is a valid Cython code. And thanks to the static typing, optional static typing, the compiled code can get rid of all the unboxing operations at runtime. And by the way, while I'm going through the presentation, you can always interrupt me and ask questions if some stuff are irrelevant or are not clear enough. So an example how static typing in Cython works. So the left-hand side is a Fibonacci function in Python using memoization and with a simple for loop, basically. And the right-hand side is a Cython with some static typing. We have just cdef AA and cdef int I. That's it. The rest is the same. And only this line changed, these 2 lines basically, well actually it's 50% of the code, it's 4 lines of code in the end. But that results in a speed up from basically going left to right in 73 times for n equals 90. I just borrowed this figure from the book because it can just depend on maybe the architecture also. And then that basically comes from heap versus stack allocation, iterator versus C loop, and unboxing versus lack thereof. And I will come to that one when basically I will just compile using the Cython compiler now and annotate what happens there behind the scenes. And by the way, I picked Cython. Of course, there are a lot of different libraries in Python that helps you interface C and C++ code and in an automatic manner. And unfortunately, Cython doesn't do that. Sorry, yeah.
Yeah. So do you have a comparison with PyPy? Because I mean, this is a very tight loop, so I think
Yeah.
Jet could do a decent performance.
Yep, I haven't tried these things, but of course, this is like a simple cookbook example. Maybe you're right. But I haven't tried that one. So yeah.
I was wondering, because Python has these type annotations now, right? Can you use that instead of the C def?
Yes. So basically the question was, what about the type annotations in Python, the language? Well, you're right. And again, maybe that would be even more relevant to this one, maybe to compare. But Cython has more beautiful stuff than just these type annotations. I will come to that one. I mean, it will just give you almost all the opportunities in C and C++, including standard template library. So you can use standard template library and algorithms basically in Cython code. And when you compile it, it will automatically choose the C++ compiler that supports it, hopefully in your platform, and then compiles it as a C++ code basically. So I was going to also tell a bit about of these other libraries, which I'm not aware of that much. You know, I haven't used that much. Why I chose this one was because of the flexibility it gives you. I mean, you can mix and match C++ code inside Python. I don't know if that's a good idea or a bad idea, but still, in the end, it helps you design this library in a neat way, and then using also shared pointers or unique pointers. So basically this smart pointer mechanism in the standard template library inside Cython, you don't need to care about the two language boundary. So whatever is allocated in the C++ or C side will be there, and whatever happens in the Python world will be living in the Python world, and then it will just mix and match really beautifully. That's why I think Cython is nice. So let's try to annotate this one, using this command. The pyx file, it's there. Maybe I don't need it now. Oops. The two codes. So basically, Cython, when it compiles the Cython file, this pyx file, it gives you with this annotate switch, this annotation HTML file, and we can check what's going on. So the darker the yellow lines are, the more Python interaction we have. Which means if you use these functions or line locations which have dark yellow lines in loops, then we will have the bad performance of basically Python-like languages. So what's going on? I mean, if you click, this is behind the scenes of Python, what it does or CPython, the C implementation of Python, what it does, just entering the function. And then here, basically, we say, well, it's a range, and I'm just going through the range, but it's really dark because of this. So what's going on behind the scenes here is that because of the dynamic typing system, this range and creature can be anything. So Python cannot give guarantees as to what range is, and therefore what I could be. So at every iteration, it tries to understand what I is, and then it tries to unbox the correct value from there, and then finally it returns the result. So here there's also another problem. Even if we are working with float objects here, 0 and 1, in Python world these are heap allocated structures boxed in the Python object. So this unboxing also happens there, and even worse is temporary variables are not destroyed in the stack. It's from whenever a temporary variable is allocated or deallocated, it's a heap allocation or deallocation in the Python world. And what happens here is basically we just annotate that n is integer. So at the entrance of the function, Python just makes sure it has something. The function receives something that is convertible to int, and then it converts to int, and this int is the C int, by the way. And then we define that a and I are doubles and integers. Well, of course also b is a double. And then now, because Python knows n and I are integers, this range n is converted to a plain old C loop, and that's where we get the benefit from this one compared to this one, around 2 orders of magnitude, roughly 73 times faster code. So this is what happens. And then here basically Cython annotate fib_py_x basically just generated the C code for us with an annotation HTML file, but we need to also compile it into a module so that we can use it in the Python world. And then if we run the other part, so Fibonacci's setup, build the extension right now in place, and that's it. So using that generated C file, Python generated us an extension module, which we can then use in this simple application file. So basically from Fibonacci Sci, I would like to import both versions and then run them together, and then that's it. You get the result. So the setup for this one is using distutils by default, or the recommended way of compiling these Cython packages is via distutils and the Cythonize command from Cython build, basically. And it's easy. In a setup method or function, you use external modules, Cythonize, whatever your Cython file is. And here, basically, you can also put include directories, library directories, other sources if you're going to mix and match C and C++ code, which I will come to later. And then it will just do the building accordingly for us. So that's it. So far, so good. Yep.
So let's track a bit. So this compiled Cython, is this usable from CPython, the extension module?
Sorry?
So what you compile there,
Yeah.
it's Cython. Is this extension module going to be usable from CPython?
The Cython command just generates the C or C++ for us.
Then you generated an extension module. Is that an extension module?
Using this setup py, yeah, is the extension module for CPython. Yes. So if you want, like, we can also go check the C file, or maybe just a bunch of them. So it generates efficiently this C file that hooks into your the Python API, and then does things efficiently and cleverly, or compared to a maybe standard handwritten module. Not an export one, maybe, but I don't know. So I've already shown you cdef double and cdef I and int, and we can basically use a lot of cdefs in the Cython world from C, And I've just listed a couple of examples. So we can either use in the block form or just line by line, and then it can support integers, long integers, or float, whatever the plain old data types are. Of course, pointers or double pointers or arrays, alias types are there. So if size type is an alias type there, we can use it as well. And then it can use structs and unions, struct types and union types to define these variables. And it can also allow for function pointers and function pointers to function pointers and so on. So all these complex stuff we can do there. So there are a couple of differences. So from C, we cannot use the static keyword. Static is not allowed in Cython. And then dereferencing pointers is always via indexing. So if this integer pointer p is only pointing to one variable, like not an array, still we need to have p of 0, because the asterisk in Python is basically splitting arrays or lists. So it is reserved for that, right? That's why we have to use this one. And then member access for structs and or for either pointers or normal structs is always via the dot operator. So there is no dash greater than operator in Cython if you want to have member access. So these are how we define these were how we define variables. We can also define functions using cdef, and basically in Cython world there are now 3 different function definitions: cdef, def, and cpdef. Basically, cdef functions are only available to def and cpdef functions from within the same source. Because they're compiled from the same source, they can be reachable from all the def and cpdef functions from the same source. Well, there's also you can also use definition files, which I will not touch in this presentation, but you can also make any cdef function available to any other module using definition files. Then def functions are available to Python. Basically, when we compile the module, from module we can import def functions or cpdef functions, but not cdef functions. So in this case, if fact is the module name, we cannot import cfact into a Python world. But we can definitely import rep cfact, which in turn uses cfact, the efficient call internally, and we can use it in the Python world. And here there's a catch, because Python does not allow for method overloading. The function names have to be different. So here we have to have a different name for the C version of the file and the rept version, basically. And cpdef's task is basically to just make them happen both at the same time. So when we write cpdef function, and we can annotate also the inputs and outputs, basically Cython generates CPython both in the C world and the Python world for us. And then if we call it from Python, we will have basically a rept version available with the same name. If it's called from the Cython world, and when I say from the Cython world, I'm just talking about PyX files, then the C version of it will be called. So there won't be any Python interaction if we are within Cython. And I hope this will be more apparent in the demo section, where I will show a lot of code, basically. Yeah?
When you write cdef, do you need to type annotate everything, or is it possible to leave some types out?
No, because we're in the C world, we have to type annotate, and in this case, if we drop this one, it's going to be void, I think, because of C semantics.
And
so
there's no type inference or...
I'm not so sure about cdef, but Cython has compiler directives to basically automatically annotate types or infer types, try to infer types at least, which is off by default, which we can use, but I'm not so sure if it also applies here. Yep.
I'm not really exactly clear on the use case. It seems like you want to use this if you have Python code, you want to speed it up, you add these So it's not so much for interacting between C++, it's more for speeding up existing Python code.
I think I will come to extension types later, and also some interfacing section there. You can also interface C files directly, and the good part is they are compiled together, so that the headers of the C file and the libraries are compiled together with the module. So there won't be any function call overhead from your module to the C, if you wish, from Python.
Type annotated Python code. That's more. I mean, as a C++ programmer, I would write the extension stuff in C++ and call it from Python.
Yeah.
This seems to be more for optimizing existing, or if you're not comfortable with C++ and you want to speed up your.
In the demo, for instance, I will use stat vector from C++ inside Cython without calling any other C++ or C library. Normally, FFI also handles these type of stuff, but there will be function call overheads, and in these loops it will be adding up. I mean, if you have double loops, in this case ray tracing, it's a matrix, and you will have these penalties. So I think here the catch is to avoid all these unnecessary calls if possible. But I'm not so sure if I could answer the question properly. Or
when you are programming like this, you're somewhere in between. You want to program in Python, but you still want to have the speed of real types.
Yeah.
So I think maybe I can answer a little bit.
Yeah.
So one use case at least is to where you want to wrap C library or C+ library and provide it to a Python program. If you're using the CPython API, you have to do all the manual work of actually doing reference counting and so on that Python does, which becomes painful very quickly. And with Cython, that take care of all of that. So making the boundary between C and Python is much easier when you have Cython in it. That's kind of.
So these are how the functions are defined. And then we also can define structs, unions, and enums, or declare them using again cdef and struct. So the familiar notation, and we can also write C-type def struct and such also in the Cython world like this. So basically, step by step, actually, I'm coming to how to wrap these libraries in C or C++, because the language also provides them for interfacing or wrapping these libraries in native Python types or extension types. So structs, unions, and enums are like this in block form. And basically, structs are, when we define a struct in Cython, then in Python world, the names are also available in the function or in the constructor notation. So we can just change their names and then write their argument names and then call it however we like. And then we can also give dictionaries to basically fill up the structures. The same correspondence also happens between standard template library of C++, so containers like containers of C++ template library. Vector goes to list, and then maps and unordered maps go to dictionaries and such. So there's this correspondence that is handled for us behind the scenes too, if we want to have it in Cython. And then aliasing, type fusing, and typecasting are also there. So basically, among them, I think type fusing is the most relevant for C++ people, because here we are now getting to templates, if you wish. So we can fuse any set of types in a type name, and then we can define our functions accordingly. And then, of course, they have to match now in terms of type. So it cannot be my double and my float. They need to be the same type, or integer in this case, because it is only defined for doubles and floats, the fused type annotated function. And then finally, the extension types are, I think, important, and that opens up a lot of options for the Cython developer to interface, either interface C and C++, or write stuff and then push it to the Python world, to the user in the Python world. So assume that the particle is an object, is a class of an object, subclassing an object, and its initializer is here, or constructor, and there's this get momentum defined, which is mass times velocity. Everything is the same if we are writing Cython, except for the cdef declaration in front of class, and then some annotations. Again, because these are cdef, normally they are not available in the Python world, so you cannot have you cannot create a particle object and then object dot m or p or v. It's not allowed if we don't write anything. But if you write read-only, it's only available in Python for reading purposes. And if we annotate it as public, then that variable m, in this case, will be open to the user of Python, basically. And then this is what I said. There's also special methods called cinit and dialog for basically handling heap allocation in the C world. So cinit is where usually we have either new operator in C++ or malloc in C, and dialog has the delete or dialog correspondence in C++ or C, that code. And then extension types can have cdef, def, and cpdef methods, of course. And cpdef and def methods can be overridden from Python classes. So whenever a Python class subclasses a Cython extension type, it can override these methods if they are annotated either def or cpdef. Then we can do a lot of different stuff. For instance, when you have a fast library in C, you can do callback mechanism easily by just subclassing some callback object with an API you design. So using all these type definition properties, we can interface C and C++. So interfacing C requires, of course, some header file interaction, and that is handled with the cdef extern keyword or block, basically. Cdef extern from some header h opens a block, and then we just pick whatever function prototypes we are going to use in the compiled code. And now we are entering the already compiled C library with an API. But there's a catch here. So this block does not import anything automatically to Cython. So we still need to write them manually. And if you make a mistake, there will be link time error afterwards, because it doesn't check at compile time what happens, or if this one is actually in the header. What it does is basically it injects this include header h statement in the generated C code, or in the case of C++, in the C++ code, and then writes generates the remaining C or C++ code. But then when they are going to link against each other, the link time problem happens because we are not careful here. If you're not careful here, then problems happen. And then the macros can also be defined as functions or some variables in this sense. So in the original header file, this was a macro, and then this was a macro. So define statements and define statements, basically. And then in this case, from C, we cannot use volatile and restrict in the Cython world. And const is supported, but is only used for type defs and return values of functions to generate correct code so that it compiles. And because of this reason, it's not needed for declaring function arguments. So function arguments cannot, you don't need to declare function arguments as const float if it's const float in the header file, because we are passing anyways the variables directly to the C world. So it doesn't change anything from the in the Cython world. Yeah.
Does this mean it uses CNAME mangling?
Pardon?
Does this mean it uses CNAME mangling, which is basically doesn't check the type of the parameter when you link?
I guess that I don't know.
It generates C++ code, but you don't know. Yeah, okay.
Later on, you compile the C++ or C code, basically.
What decides if it's C++ or C that's generated?
I will show it also in the files. So there's a directive. You just say language is C++ if you're using C++ things. By default, it's C. Any other questions? No. And for the C++, on top of what we have in the C semantics or these declarations and type defs and such, we have an addition to the extern from block, which is basically the namespace. So if you're working with C++ libraries, then we can also annotate the namespace or choose the namespace. And if there are nested namespaces, then we will do colon here, like the new C++ supports. And then the rest is similar, but now if you have a C++ class, we need to use cdef CPP class if we are going to use the class declaration from a C++ header file. And then we can use a standard library like in this way, and we can define exceptions if the function is not no except. So if we expect exceptions, we can also annotate it. Here, for instance, this is this constness or not needing constness happens. Basically, the return type is const, and in the C++ standard, I think these are also references like const reference, and const reference. You can put references here, and you can put const, but it doesn't change in this setting the way Cython compiles. Or Cython already has the libraries imported like this way. So from libcpp.vector c import vector, we'll just import the vector from standard template library for us to use, and then we can just define vector of integers like we usually do with the cdef. Then some code, like how these things go in together in a Python file, if there are no questions. And yeah.
Oh, the one question is, this is like learning a new language with a lot of quirky rules. So I doubt any C+ programmer want to writing the code in this way.
Yeah, you might be right, yes.
It might be good for you have a large Python code base, you want to optimize the part. But for porting C++ code in this way, that's a nightmare, really.
Well, it's not porting C++. Again, like if we go back to this Fibonacci example, annotated version of it, I mean, Cython also provides a framework to tell if you are using Python or if you have to use Python at some point, where the bottleneck is in terms of computation, like where you lose a lot of time, and whether you can optimize these things with these things. Like, for instance, this code, when written in Python, will be so short, and maybe with a couple of cdef additions in the hottest areas in these loops, you just get some speed-ups. So, and then there are also other problems. If still you're using Python, for instance, when you want to use a C++ or C library that has multi-threading support, because of the global interpreter lock, you have problems. But then in Cython, you can also avoid that one easily. You can define cdef functions with no global interpreter lock, and then you can do multi-thread parallelism behind the scenes, which is going to be way easier. So it depends, I think, on the use case.
Yeah. And if anything goes wrong, it's really hard to hunt them down and debug it.
Well, you have the debugger in the end, right?
Yeah, but this is cross multi-language.
Yeah. So it's an example in the first book between 1 to 6 chapters, and then it's gonna be creating an HD image and then locate the camera one unit in front of the scene, and then put two. In this case, it's two spheres, and I will try to add 10 spheres as well, and calculate whether and if so, where the rays hit the spheres, and then fuse the or using blending, color the spheres. Now I need to go here, and maybe here. So the Python code, and this code I borrowed directly from the website. It was a C++ code. I just verbatim copied and did the Python stuff here, and it's this much this many lines basically. So it has a vector3 class. So it's basically a fixed size three-dimensional vector, and then it has the operations they need for this project. So addition, subtraction, division, multiplication with a scalar, and multiplication with a vector, and then the length of a vector, which is basically the norm of the vector, and then make a unit vector out of a given vector, and then make the vector a unit vector. And then ray basically has two vectors. So basically array goes from an origin and points to some direction. So for this reason it has the direction vector and the position vector there. And then the dot operator is defined between two vectors. And then I need to create some struct here, and for that I used data class from data classes. And then there is a hittable object which defines some hit function, and it has to be overridden in the subclasses. For instance, sphere is a subclass on a hittable object, and then it has a center and a radius. And then to calculate the hit, basically it gets the normal where the hit point occurs, and then it tries to solve a second order equation, one variable. It's simple, and by just looking at the discriminant of this equation, it tells whether if it's a hit or not, and if it's a hit, what is the closest location to the eye or to the camera. So if a ray intersects at the tangent of the sphere, there is one hit point. If otherwise, it will be 2 points. So one close to the ray, one close to the camera. And then the closest point is important, because then we will have this 3D-like scene when the objects are placed. Then the author in this website chooses to implement hittable list as a structure of arrays, basically. So it is a list of hittable objects, and for each hittable object it calculates, and then it just reports the closest hit point. And then you color the ray given the world, given the objects basically with respect to the scene. And then finally you generate the image and then save the image. So the timings I have are here up until this point. Yep.
I blinked for a second. What did you say about the data class directive up there? The data class annotation? No, it was further down. The data class, that thing.
I just wanted to have something similar to C struct with annotated types and such.
So that kind of skips the constructor work.
Yeah, I guess so. Yeah, I mean, I guess this decorator does that. Yeah. So then, so the left-hand side is what I've shown you. Right-hand side is the Cython file, and the only change is the first line. In the with a directive, you say, "Hey Cython, language level is 3." So Cython by default generates for two Python languages, Python 2 and Python 3. And I want to keep focus on Python 3, and that's what I said. And because I haven't done anything yet, I don't care if it's a C file or a C++ file. And then Cython compiles this. Maybe. Oop. Right now we are compiling them for extension modules, these files. And as I said, the only difference was that one. So without doing anything, well, maybe, oops. So I have the timing files like for Python and Python for the compile one. It will not finish before my talk, I guess, because of Python. It takes a lot of time to do that, but I can go over to the other file. So the other file, now the left-hand side is not annotated, not done anything, Cython file. So just the directive Cython use language level 3. So generate me Python 3 or CPython 3 code. But the right-hand side is a couple of CDEF declarations here and there, so that I'm just hinting the compiler to use as much information as possible to generate efficient code. So in the first one, because I'm going to use a vector from C++ standard library, I'm also telling distributors to use C++ as the compiler. That's why I'm annotating language as C++. And then again, the class is just a CDEF class now. And then these defs are CPdef because I want to use them as efficiently as possible in C, but still make them available to Python world. Nothing has changed there. And then these magic functions or special methods are not C-defable. They can only stay def. But I can at least annotate what index is or what value is beforehand. And then the multiplication is a different story. So basically in Python there's mul and rmul, the reverse multiplication. So if the first one doesn't apply, then it changes the order of the operands and then calls rmul instead. But in Cython it doesn't have it. So Cython only has mul. Then you need to make sure which instance you're working on in an if statement. And that's the only difference here. And of course rmul is commented out in the right hand side. Then the length of a vector is basically returning double, and then making a unit vector from a vector returns also a vector. And then here make unit vector, I'm dividing by some double and I want to use C division rules. Basically this means, okay, don't touch this part in the Python world, don't check for division by 0. Let C do its job properly there. I just want to have C semantics in the division. Similar things here appear in CDEF class. The only difference here is basically I tell in advance what A and B are. They are vec3. And then the def statements are CPdef. So basically it's not that of a problem to help Cython to do its job and then all these for loops, I want to have C loops. That's why I need to annotate indices with integer types. Everything then flows like this, and then the hits are again like the logic doesn't change. You just write in Python, but you just annotate above what the types of the values are. And then in the generate image, I tell here using these decorators, I don't want any bound checking on Python objects. So I know what I'm doing because I'm writing in C and I don't want anything there. And then I don't want wraparound. So basically negative indices are undefined for me. But in Python, it will just rotate back. So I don't want this one. And again, I want to have C division semantics because I have double for loop below, and in this double for loop I have division by numbers, and then at each iteration, if we don't turn it off, Python checks whether there is division by 0 or not. Here I don't care about it because division by 0 when it comes to doubles are fine for me. I will get inf or negative inf depending on the other number.
What does the Python do if there is division by 0?
It throws, yeah. And that's it. I don't know if the code finished. No, it's still running. in the end, it will generate this one. Hopefully, we are still waiting for Python because it hasn't reported yet. And then, yeah, I was going to put maybe 10 more spheres, but it will again take even more time for Python because right now there are 2 spheres in the double for loop. So if you have 10 spheres, then it's going to be multiplying the double for loop by 10 instead of 2. So it's just adding up. But in short, I can give you some timings. So the first version here, so from left to right, only adding Cython declaration and compiling it has given 50% improvement. So basically from, let's say, 160 seconds to 80 seconds. And then the type annotated version here, the right hand side, and I think they have similar, yeah, there's only 2 more lines here on the right hand side. So not much of a difference. And this one has given, with respect to the first version, 1 order of magnitude. But the good part is it's not there yet, and I know why it's not there yet. At least when I annotate this one, it shows directly that, hey, these special functions under add, under mul, I am spending a lot of time there, so they are really dark yellow. Then it means I need to just replace them with just proper cpdef functions, and I need to call the methods there. Then of course I will not be using maybe this type of plus and multiplication between vectors, but then I will get up to maybe 2 orders of magnitude improvement in the speed. And then I think that is all. So basically, Cython is a language that extends Python with static typing features, and it has this compiler that generates efficient C and C++ code. Then overall it provides a nice framework to focus on the parts of Python code to be optimized. So maybe if you're writing Python, you don't need a C++ library. If you can optimize a couple of loops, especially in this case nested loops, then maybe you're already good to go. And it helps tightly integrate with C++ libraries because it generates the C++ code with the C or C++ library you're using with, and then compiles them together if you have the headers. And it has some more neat features like exception handling. I've just shown a small line. P-range for multi-threading purposes, but it's mostly for embarrassing the parallel stuff. And then no-gil and other constructs that are available when you want to get rid of the global interpreter lock or keep it. And for definition files for code organization. So in the beginning of the talk, I said some functions are available only in the source code, but you can also export them using these header files, pxd files, and then any other Cython module will be just calling these C files as efficiently, even if they are different modules. And with that, I just thank you for your attention. Still running.
Question?
Yeah.
What happens if you call from Python with a wrong type during runtime?
It's a runtime exception from Python.
Ah, okay.
Because in these type annotations, Python tries to unbox them and then cast it to the proper C type. And if it cannot do that, it will just runtime. Create a type error, not runtime, sorry, type error exception.
Ah, right.
Yeah.
So actually it's the same thing as in a type annotated pure Python
Yes.
world. I thought that was only in the linting tools. I guess I don't know enough Python.
No, I don't know. Yeah.
So how far will the optimization go? Will it unroll and use SIMD instructions?
I haven't checked that one. I haven't tried that one, to be honest. But the thing is, when you check some of these for loops, they are already simple enough. And if your compiler supports it, you can always attach compiler switches to the setup py, so that it can ask the compiler to generate if the compiler finds it sane. But I don't know if you can hook in directly your own intrinsics.
said you took the algorithm from a C++ source originally, right?
Yeah.
Did you compare what's the performance from that?
There was a bug. I need to first maybe report and fix it there. So it was a bit of a problem to have this up and going, but I will do that. And I'm planning to push this one on GitHub in a public way, and I will report these things. Maybe, I'm not the writer of either Cython or author of this ray tracing, so I don't advocate for either of them, but I think they were both cool, and I'd like to do that, but I haven't done yet.
How fast does it render the image with the Cython compiled stuff?
The type annotated version, which is two lines more code, but maybe in many of these lines we had cdef statements, it is running 13 seconds.
Because in C++ you can write something that renders it in a few nanoseconds, basically.
Yeah.
If you optimize C++ code.
Yeah.
And have you compared this with Numba, for example?
No.
Python?
Again, there are a lot of maybe Swig and other libraries. So
Numba is super simple. You basically just import an annotation, and it will optimize it to basically.
To be honest, I mean this example This example is already a matrix operation. I would use NumPy for that one. It would have been the fastest, I think. But yeah, it's just trying to understand what and how good Cython does these type of things. Plus, the annotation really helps focus on the important parts in that sense.
I'm genuinely curious because I come from the C++ where I haven't done much Python. So for me, the answer is obvious, but it might not be for everybody. Do you think the Cython version is easier to read and maintain than an actual C++ version?
I'm also comfortable with C++, so I don't know. And I don't know much Python either, because my colleagues are using Python a lot. So I like to use Python and Cython. Normally I use Julia more, for instance, but I'm for the compiled language. And for me, the modern C++ at least is easy to read and maintain, but maybe I'm biased like you. I don't know.
I guess your colleagues' opinion on this would be interesting.
Yeah.
We have another question.
Yeah.
Sorry.
You? Okay, sorry.
Okay.
Sorry.
So I think I can sell Cython a little bit maybe, because there is a use case where, let's say you're working on a C++ library and you have other people in your company using Python that don't know C++, and they want to interface from Python to C++, and you don't want to handle CPython's interface or do any kind of work. Let them do the work. Then you can give them Cython. So they can write basically Python code and they can interface to C++ efficiently and do efficient things with your C code. But you don't have to get involved. You can stay in C++.
Yeah.
Nice.
The best part is, I think, the pointers. Like using FFI, defining pointers or pointers to functions are a mess. Here you just write cdef, whatever pointer type you have, or pointer to function type you have, then you're good to go. And then you just define your callbacks easily. That's, I think, really helpful.
I guess those are the two use cases, for interface code or for speeding up existing Python code.
Yeah. Yeah. Yes?
So what is the benefit above PyBind, for example?
I haven't tried that one.
Because that is actually built in, you as a C++ developer use it to actually build the interface to the Python guys. So you decide what is public or front-facing instead.
I have just experimented with Cython. Again, I'm not a super good Python person, and when I tried, I first researched what is available in the language itself. So FFI was there, so I haven't even checked other options. I just wanted to have something first from the language itself, and then maybe search for third party. Yeah. So you had a question?
Well, kind of. I was wondering about the compatibility with the Python libraries from Cython. Like, for example, when I looked into such options, it seemed like a year ago, neither Python nor Cython seemed to be compatible with TensorFlow, for example, directly. But I guess you could probably just put your code, Cython code, separately from your TensorFlow code.
NumPy is written in Cython. So NumPy has, I think, according to the book, if I'm not mistaken, 10,000 lines of Cython code. So it is written in or maybe it was Sage. Sage has, I think, 10,000, but NumPy also had it. And CyPy is now moving towards, or has moved towards Cython. So basically, for me, the three most important libraries are there, and then they're using it. And TensorFlow, I don't know. Maybe you're right, but at least these three major libraries are using Cython. Yep.
Okay, then we will start now with the break.
Thank you. Python finished. It's the 10 simulations, that's it, or 10 trials.